All right, I didn't really change the lights in our other activities, but lights are officially now green, so floor is mine. Let's jump into our lesson today. If we do so, we should have time at the end where you actually get a little bit of time to actually work on the homework in class, which is like a rare miracle. But it happened last period. They had about 15 to 20-ish minutes to work on stuff, so let's shoot for that same goal. With today, our objective is we're learning how to write a rate law of an overall reaction from a mechanism. So on our first day of the unit, we learned how to write a rate law from data. So let's review really quick just the basic format of any rate law, right? So a rate law is a full expression, right? This is going to be a common question on the test of finding rate laws. So rate laws are always rate equals K. What does K represent? What is it telling us? Yeah, it's a constant. What is it like there for? What does it take into account? Temperature. Right, so that's a key thing. Thanks, Leah. I was my face then. This is our temperature varied constant. Right, so it helps us see that if temperature goes up, K would go up, and so the rate will go faster. Okay? Then it's always brackets of things, and they're only reactants. Right? So products are not included in a rate law. Right? It's only the reactants. And those reactants will be to some power. I'm labeling them M and N because that's how it is in our first talk about them. And these are the orders of the reaction, or they help us understand how does A influence the rate, or how does B influence the rate. Okay, so all rate laws have this generic setup. With our orders, we found them the first time around with those big data tables, and we look and see, okay, I doubled A, the rate also doubled, and so that told us A was first order. Or B, I doubled B, and the rate quadrupled, so it told us B was second order. So that's the first way we learn how to write a rate law. Today we're learning how to write it from a mechanism. Now, there's still experimental evidence behind the mechanisms. It's just not as mathematical looking, but recognize it still comes from data. All rate laws have to come from data. Okay? So with our rate laws and our mechanisms here, we know that a mechanism is breaking it down into the steps of the collisions, right? Things are colliding. This collides with this. Then this collides with this to actually get the product we want. Each step is always written as an elementary, which means only one collision is happening, right? That's the rule of steps. The step is only a step if it's one collision. If a step is more than one collision, then it has to be written in multiple steps. Right, so the idea of a mechanism is breaking it down into steps. Now, with those steps, through experimental means, scientists can label what we call the slow step and the fast step. Or if there's more than two steps, you can have 3 fast steps and a slow step. Okay? The name of the slow step is known as the rate limiting or rate determining step. We're going to learn and focus on today that it's all about the slowest. So to give us kind of a silly analogy to maybe help us remember, we're going to make a 4x4 team out of our class. Oh. Now for those of you who are like, what are you talking about? Yeah. Okay, so here's your mini track lesson for today. Okay, so the 4x400 meter relay is the coolest relay there is. It means each person runs 1 lap around the track, right? And as a relay, like you hand off the baton. Swimmers, it's like equivalent to like the 4x1. I'd say it's like pretty similar to that. My swimmers in here.
We should actually do it. Good example.
I am so down.
I guess at the end of the day,
I am ready for a 54.
4x1
so ready.
So
If we have time, we'll do it.
okay, who wants to be on our, we're not going to make you run, it's just for purposes, but who wants to be on our relay team? Okay, Bryson, you're going to be our lead.
I'll anchor. I'm an anchor.
Okay, so there's a purpose to this, everybody. Stay with me here. Bryson, how fast can you run at 400? Pick any number you want. If you have no idea.
Laura said 82, so I'm gonna go.
82 seconds. All right.
Oh, well, that's really slow.
No, that's like, I think that's like, that's respectable. That's under a 6-minute mile pace.
Oh, great.
Whoa.
Yeah, I think it's pretty respectable for
Pretty fast.
an average human being.
It's all 'cause-
Okay, who wants else to be on the team? Okay, Jack. Jack, how fast are you gonna run a 400 for us?
Run in 81 seconds.
Okay.
Can I change my number to 80?
No particular reason, you know.
I-
You picked 80.
Yeah, no.
Okay, who's our third leg? Who's our third leg? Okay, Gavin, how fast?
You better have me anchored.
I can do it in 1 second.
Wow.
Okay. All right, we're gonna have Rhodey be our anchor. Rhodey's gonna run it in
Are you gonna do it?
10 minutes.
You know it. You know it.
Okay, now I only pick on him because I know how fast he truly can run it. If this is our relay team, who is truly limiting our ability to succeed? Right?
That's me.
Even if Bryson's like, oh, I'll run faster, I'll run an 80 today, is it really going to help our team much? Not really, right? So this is the idea
Devin will run a 0, don't worry.
of our, oh, you should have seen the relay last period. They were running it, like, the first 3 was like, I'll run 3 seconds, and then the next person went 0.3 seconds, and the next person went 0.03 seconds. And then Ian ran it in 10 minutes. So. But this is what I mean by the rate determining step. Is it, the other ones almost become not even part of the process because that's the one that's limiting how quickly it can go. Once we get Zach faster, then everything else changes, right? Now in our case, we can't make the slow step go faster, but it is gonna be our focus of where we write the rate law from, okay? So our focus today is helping Zach everybody, okay? Oh, let me clarify this too. So with our graph here, we saw these last time, right? Remember our double roller coaster? Each hump is for a different step. Keep in mind, it's written on your notes, but I realized it printed a little fuzzy. Make sure you emphasize that this would be a second, the slow step would be second because this activation energy is so much higher, right? So this is where the slow step is second, and the fast step would be first. Okay, let's look at an example of writing an overall, okay? So here's our mechanism for this reaction. Now, I could write the overall reaction, and maybe let's practice doing that, because then we can prove a point here. So if I write the overall reaction, this is the same problem we did last time. Right, so I end up with NO2 gets canceled, NO3s are intermediate, so my overall reaction ends up being NO2 plus CO, turning into NO and CO2. So just like from last time, writing that overall reaction from a mechanism. What the question wants us to find, though, is the overall rate law. Okay, so we're trying to find the overall rate law for this process. The overall rate law is always about which step? The slow step. So in our case, now the slow step will always be shown to you. I forgot to put it on my PowerPoint, but on your notes it tells you which one's slow and fast, right? That has to be given. There's no way for you to look at a person and say how fast they're going to run. Right? You can be very deceived. I've stood next to people, you can guess, but I've stood next to some people and like vice versa. I'm like, whoa, they look like they're going to be really fast or not, and then they can surprise you. So same thing with reactions. This is going to be given because it's determined in a lab. Okay? All right. So since the slow step is first, once I get past it, the reaction can go. So our overall rate law is going to be the rate law of the slow step. So I write rate equals K. So same format as always. I'm looking at my slow step only. So my slow step is NO2, right? And two of them, so I can write it as NO2 to the second power. And that is my answer. The overall rate law is the same thing as the rate law of the slow step. Yeah, Alex.
So what if every step was relatively fast? Like you had one that took 3 seconds and one that took 5 and one that took 2. Like changes in those would make a big difference compared to
Good question. So in the end, like, and the keyword I like how you use is relative, right? Like slow and fast are totally relative terms, but in the end there's always going to be the slowest. And so it's still going to determine how quickly or slowly it goes, right? Even if it's not as drastic of hills, right? Like maybe the activation energies aren't that different from each other, but whichever one has the highest pretty much is still going to govern how quickly it can go. Does that make sense? Yeah, good question. I have a smiley face for that. Okay, let's try one for smiley face for everybody. So given this one, so scoot down to the next equation below, write me the overall rate law for that mechanism. Once you have an answer, compare with your table, and then write an answer on your boogie board, and then raise your hand. I'll come check it off for a smiley face. So write me the overall rate law. And compare with your neighbors. If it matches, you're going to have one answer as a table. And I'll check it off.
How do we know if we're squaring this We're crazy, we're insane.
Yes, that's my face. Yes, you guys do good job.
Why do we get to the part where I didn't even do that.
From where it started. Well, that's like
Oh, so you're saying. That makes sense.
That's what we tell each other. I'll take as many battles from this day on. Wait, Jamie, so for me writing the fact, just like oh, yeah. How many that was super dry. And then just what kind of
That's a good question, Zach. I don't know. Did I check yours already? No. That is correct. Good job. Have a smile.
Yes. Let's go.
All right. Nobody wants to check yet. Should we bring on the cookie board as a team? There's no secret. I just got excited for so Yes, have a smiley face. Yes, have a smiley face. All right. Good job.
really? Yeah, dude.
I did not know that.
Okay. Well done. With this, I want to emphasize something I forgot to emphasize with our problem above, and we're giving your eyes this week. Okay, boogie boards should be home, which means they're in the middle of your table and they're sleeping, so you're not drawing on them. Okay, from here on out, if we are using them when we're not supposed to be using them, okay, I'm going to treat it as if you're on your cell phone. Because it's the same thing to me as you're being distracted from what we're trying to learn. Okay, so keep them away when it's time to use them, or if you're just waiting, right, like if you're waiting, right then was a fine time, you got yours checked off, you had nothing to do, you can doodle on them. Right, but don't distract you from what you need to learn. Okay, from our problem before, I want you to emphasize this. This was our overall rate law. Does this match the overall equation? No. Because overall equations you can't write rate laws from. because it doesn't show you what really influences the reaction, right? From this, in a sense, CO is a reactant. It's not here, so what does that mean about CO? It's zero order, right? But keep in mind, the overall reaction doesn't show that this is second order or that that is zero order. So make sure you keep in mind as we write rate laws from steps that you don't deceive it as you're writing it from an overall. You cannot do that. Maybe every once in a while you might get lucky that it happens to match, but you can't write a rate law from an overall reaction, okay? All right, let's take a look when our slow step though is not first. So things change a little bit when it's not first, but it's still gonna be the focus. So the problem is that when the slow step isn't the first one written, what happens is now you start having intermediates pop up. And intermediates cannot be present in an overall rate law because the overall rate law should only be based on reactants. And so we have this issue here of intermediates start coming when the slow step's not first, but they can't be there in our end answer. So we're gonna have to do a little bit of substitution in the end. Okay? So go ahead and I'm gonna just go to the next one because then we can look at this and write on it. Okay? So, same as before, let's write the rate law for the slow step. Okay? So I'm writing the rate law for the slow step because slow step is where it's at. Okay? In our case, slow step is second. So my rate law would be rate equals K, and then there's NOBR2 and NO. So just like we just did, looked at the slow step and wrote the rate law. Questions on that? Now, last time, this was our answer for the overall because the slow step was first. Our problem now is NOBR2 is an intermediate. Let's go with right? So this is an intermediate, right? Because it was made here and then used there. I'm going to use different colors very specifically here too, so if you want to use your highlighter with me, you can. Okay? So intermediate can't be in the rate law, right? This can't be here. So I need to replace it with something that it is still equivalent to, right? Because I don't want to change the values, but isn't represented as an intermediate. So the other thing that's always going to be there whenever the slow step is not first is you're always going to have this interesting double-headed arrow on the step above. Yeah?
For the rate law, do you need to write NOBR2 or just NOBR?
I meant to write NOBR2. Thank you. That 2's still there. Don't want to get rid of it. Thank you, thank you. So when the step is prior, you're always going to have this double-headed arrow. What's going on here is I almost imagine as this reaction is happening quickly. This one needs more energy, and so it's taking slow. So this reaction is actually going back and forth and back and forth and back and forth while it's waiting for this one to have enough energy to go and finish. Right? For those of you that are runners, it's like runner number 1 is doing mileage while the other person's running their lap around the track. Right? Because you're just waiting for it to go. Okay? This, in a sense, gives us an idea of equivalency. It's actually known as the equilibrium arrow. Unit 7 will learn all about equilibrium arrows, and every reaction in that one will have this, so we'll see this arrow a lot more. For now, recognize that it's a representation of equivalency back and forth. Okay? So, because of this, this is what I need to substitute, correct? Our equation says that this, I'm switching colors again, is equal to this and this. So I can write those two things in place of the NOBR2. So I'm going to rewrite it down here and I'm going to match my colors. So our rate is rate equals K. NOBR2 we're replacing with NO and Br2 because that's what it equals. Now, notice in my original one, right, I can't lose the other part that was still there, so I still need the NO because this is all I was substituting out. Yeah, Aglia. Good, so then I substituted it so you could see, but she noticed that the NOs, like there's two NOs there, so my final answers I would actually combine them. Yep. So I'd write the rate equals K and then NO squared Br2. And so this is my overall rate law. Questions of how, yeah, Lily.
Does this only work if it turns into only one thing as the intermediate on the other side? So like where the NOBR is, BR2 is, could there be other things with that that would do the same thing?
Yes, it just looks a little weirder. Let me show you, I don't have an example, and to be honest, it's kind of rare. So like, I saw it show up about maybe 5 years ago on the AP test, but like since then I haven't seen it again. But I'll show you because it is the same concept. So give me your attention here, everybody, and then I'll have you try that practice problem because Lily asked a really good question. So Lily asked, like, does it only work because the thing I'm trying to substitute is the only thing on this side? It actually will work either way. So hypothetically speaking, if there was, let's not do blue, let's do a brown one again. If this equation had like this plus, we'll just say substance A was also created in that step, you can still substitute, but the difference is I have to still isolate this variable. But if this is like an equal sign, I can move A over by dividing it. And so what actually your rate law would look in that case is you would have, you'd be substituting NO Br2 over A is the same thing as NO Br2. So a little more complicated, but the logic is still the same. So this is my new equation. This, in a sense, was then what gets substituted in there. So, any other questions? Have a smiley face for that, Lily. Okay, try the practice problem right below for a smiley face, and we'll see how we do. Ready, go. Oh, you're missing your slow step stuff.
It's the middle one, isn't it?
It is the middle one.
Oh, yeah.
Fast, slow, fast. And once again, that will be given to you. I just messed up giving it to you.
Oh, let's take a look at that sauce. Oh, yeah. Yeah, I'm so right. Let's go. I do figure it says whenever a facet receives a low
So you just ignore the door.
When are we moving? When am I starting It's already callous in the cash.
Why did you do it?
Oh wait, that's not a reaction.
Good job.
Yeah, we did.
Why does it have to be?
Yes, well done.
That is also if you oh, so I can't tell you.
No, it's
Okay, I think I checked them all, but let's just go over really quick. So if you have this, you can have my smiley face. So your final answer should have been that the overall rate law is rate equals K, NO2, F2. You have that, have a smiley face. Just one. I just want to re-emphasize again. This is the overall equation. Right? This is the overall rate law. Right? Notice like the disconnect here, how there's a 2 in the overall, but there's not a 2 in the rate law. Right? You can't look at an overall reaction and write a rate law from it. Okay, just once again, you're just playing the game of guessing then in that case. You have to base it off of data. A mechanism is a type of data. Now, one of the questions on your homework that as we're leaving mechanisms and we're going to start talking about catalysts a little bit, I just want to address is mechanisms are a type of backed by data, but they're also like a proposal idea. Because when it comes down to it, we can't actually see these things collide. Like we don't have microscopes that allow us to watch a reaction at the molecular level and see like, oh, collided with Cl right here and da-da-da-da. So they are somewhat of a proposed idea, but then they get supported through experimental evidence of being able to isolate intermediates. Such as in our graphs, once again, notice, I'm going to go back here really quick. Right, so notice our graphs, remember that the low points are intermediates. And so you can isolate those as a scientist and be like, oh, this was created. But it's not there in the end, and so that's kind of how they know their presence. But a mechanism rate law should match the data mechanism, the data rate law that we learned how to do in the beginning. So this process is kind of something scientists do in both ways. They do the data we learned on day one of timing reactions and seeing how fast it goes. Then they say, does this match a mechanism we proposed? If it doesn't match, then you know it's a bad mechanism. If the mechanism matches, then at least it's a valid proposal. Okay? So with these graphs here, we're going to draw two in a second for some smiley faces. So what I'm going to do, you can talk as a table, is I want you to come up with two graphs for me. In this first box, you're drawing me a two-step mechanism where the slow step is first and your delta H is negative. In your second box, you're drawing me one where the slow step is second and your delta H is positive. So talk as a table and draw me two graphs here. I'll give you 3 minutes, and then we'll check them. You can look on page 10 as an example of a graph.
It's going to start right here.
Keep in mind, it's a two-step mechanism. You should be emphasizing the slow step. Look at page 10 on your notes. Example. I'd say those are both valid answers. There's a variety of how they could look.
Oh wait, sorry, that's for the second. Yes.
Mine.
Like even more like I'm about to make
Okay, 2 people want to come draw their pictures on the board. No, but Bryson likes to draw on the board. All right, Zachary, come on up. You guys pick either one, doesn't matter to me. Pink's a little bit of a struggle. You can try it. I'm like soaking the last straw so you got it. The rest of it is very vibrant. Yes, don't draw tiny grass.
I just didn't do my second pig.
Thank you. Okay, good job, guys. Thanks. Okay, looked good when I was walking around too. Just a few things I want to emphasize. When I've seen students do this in the past, pay attention here, everybody. So 2 main components on each graph, right? Number 1, the delta H tells you the beginning and the end point, right? If the delta H is negative, it should end lower than it started. Don't make that so close that like a grader has to like get a ruler out to tell if it's going up or down, right? Like not saying you have to make it dramatic, and theirs are great. I'm not saying theirs are wrong. I'm just saying that's what I've seen in the past when it's on the test before, is some students I'm like, is that going up or down? If I have to question it, then I'm not going to give you the point because now I'm questioning if you knew what you were doing too. The second thing is the height of the peaks, once again, represent their speed. Now keep in mind it's always a measure from where you were to the top. Right? So same thing here. Same thing, don't make them so close in height that it can be tricky, right? Theoretically, Bryson's are great because I can see this one's higher, but if this one was up more, even though it's lower on the graph, right, that actually still could be the slow step. So keep in mind, slow doesn't mean it's lower, it means that distance from where you were to where you're going. Alright, so if you had similar graphs, meaning start high and low with a bigger first hill, start low and high with a bigger second hill, you can have 2 smiley faces as well. Bryson and Zachary, you guys can have an extra smiley face for drawing. Questions on the graph side of mechanisms? Yes?
Does it matter that both of them
No, it doesn't have to. Yeah, you could totally have it like yeah, that is an interesting coincidence. But no, it doesn't have to. Okay, last thing, everybody. And then we're done. Let's talk about catalysts. So, with the idea of catalysts, everybody, we could spend weeks talking about catalysts and understanding how they actually work. Which we are not going to do. We're going to take 3 minutes. So I'm probably not going to answer maybe all the questions you have. Maybe we'll answer some. Might just bring up more. Sometimes that's what I found is the more I learn, the more questions I have. But the idea of catalysts in terms of what you need to know are, number 1, as we did before, they are something that you put into a reaction but doesn't actually end up getting used up. You get it back out in the end. All catalysts, there's a lot of different types. I'm going to introduce you to like 3 different names of catalysts today, but there's more than this. But all of them work through the same means. They provide a way in which you can lower the activation energy. They do this through either increasing the number of effective collisions, so sometimes they help in terms of that orientation idea of making sure they're rotated the right way so they collide where you need them to. Or, once again, sometimes a completely different path because you end up with multiple intermediates, and that's what this graph is showing. So if you want to use your highlighter to emphasize it, the black line is the original reaction. The red line is the pathway that happens when a catalyst is added. So you go from a one-step reaction to a 1, 2, 3, 4 step. But in the end, those 4 steps are still faster than the one step because all the energy is lower. And so it goes faster in the end. But most of the time with the catalyst, you get more complicated, but it's because it helps you get to the goal faster. Okay? With the catalyst, as we've done before, with our reaction, there's something you start with and end with. So circle for me really quick in this example, who's my catalyst? Don't say it, but circle it. Circle it on your paper. Who's my catalyst in this reaction? You circled I minus, have a smiley face, good job. Right, so I minus did, notice here everybody, the catalyst bonded, right? It bonded with O. But then in the end, it got released again. So all catalysts kind of like, they play a role, but then they come back out. Okay? So one type of catalyst that you might be familiar with, oh, did you have a question, Christina?
So if the step 1 is the slow step and since the I bonded with you, would you include that in the rate law?
So no, so catalysts do not get included in an overall rate law. You would exclude it out. Yeah, good question. Thank you. I forgot to clarify that earlier. So one type of catalyst you should kind of know by name, because it's just like you should recognize it's one and the same, is the word enzyme. So if you read a question and it talks about an enzyme, your brain should say catalyst, because that's what an enzyme is. It's pretty much just the word we use for a biological catalyst. So in biology, you talk about enzymes. They're catalysts for biological functions. But they work in the same context where they just help speed up a reaction. A lot of times they nickname them a lock and key idea. You may have seen pictures like this in biology class before, or you will if you take it. The idea is that here's my enzyme. Okay, here's my reactant. The catalyst binds to it, which helps in the orientation idea. And then in the end, though, the enzyme breaks off and can be used again. Right, so enzymes are always there for our body to use unless you have a deficiency and you don't have certain enzymes, like if you're lactose intolerant. Being lactose intolerant means you lack the enzyme lactase, and so your body doesn't have the key to break down lactose. And so if you put lactose in your stomach and it can't break it down, the stomach doesn't like it, and so you don't feel very good. Which is what there's other type of enzymes you can lack sometimes. It's kind of cool if you didn't know, and if you're lactose intolerant, maybe you do, for those that don't. They actually, scientifically now, we're to a place where scientists can make synthetic enzymes. So I can take a pill of of lactate, before I eat my ice cream. The enzyme is there and can break it down. Now the difference is, it is still a catalyst, but because it wasn't created by my body gets rid of it. And so you have to take a pill every time. But there's kind of a way to like artificially get those enzymes. So that's kind of the big idea. But once again, just pay attention. If a question says enzymes, just translate it to the word catalyst in your brain. Okay? Another type of catalysts are ones that happen in acid-base reactions. The one I want you to emphasize on this picture here, this is on your paper. If you turn it over. Oh, it like got cut. It like was there. That's a sad thing. Well, I guess you can't circle it very well. I guess just pay attention to here. Once again, the other thing you should be able to do is identifying catalyst. In this case, our catalyst right up here is H+. Because notice, it starts here, go to the end, and it's there again. So that's the other thing, really, with like, when you read a question, you should just be able to identify the use or where catalysts are present. But no matter how it's written, it's always the idea that it's there to start with, and then it's there in the end. Yeah?
How does H+ exist?
So what would it mean if it's H+?
It lost an electron.
Good, yeah. So
there's a plus.
yep, so it's nicknamed the proton.
Oh, great.
So, yep. And it's actually what makes something acidic. So we'll see this a lot in acid-base unit of unit 8, where anything acidic is a whole bunch of H pluses floating around, which make them pretty reactive to certain things. Yeah, good question, Bryson. All right, the last type of one I'm just going to introduce you by name is called a surface catalyst. The idea is just as it's named. You have a surface that allows it to bond to, so the catalyst is actually the entire surface. The idea of the surface catalyst, once again, is it helps with proper orientation, right? Because if I'm needing A to collide with B and like the things are rotating through the air, that can make it hard for them to collide. But if I can hold one of them in the right way it needs to, then it increases the chances of effective collisions. So that's the idea of a surface catalyst, but then in the end, it gets released off the surface. Once again, there's like 10 more types of like names of catalysts that you can use. The big thing are they don't get used up, right? I put them in, they come back out, and they do it by lowering the activation energy somehow, right? Either by creating more pathways or better orientation. So, any general questions with catalysts? Okay, all right. Homework tonight. So right now you have